Understanding statistics can be tricky, but it's crucial. One key concept is maximum likelihood estimation, or MLE. MLE estimates the parameters of a probability distribution. Think of it as a tool to find the numbers that best describe our data. We'll break down the theory, look at examples, and discuss the pros and cons. Let's dive in and explore MLE together. Before diving into MLE, let's understand probability distributions. A probability distribution tells us how likely different outcomes are. Discrete distributions deal with specific values like candy colors in a bag. Continuous distributions deal with ranges like student heights. Both types have parameters that describe their shape and spread. Understanding these distributions is crucial for using MLE. Now, let's move on to maximum likelihood estimation. Maximum likelihood estimation, or MLE, is a powerful statistical method used to estimate the parameters of a probability distribution. It is widely used in various fields such as data science, economics, and engineering. MLE works by finding the best fitting curve for your data. It does this by maximizing the likelihood function, which is a measure of how well the model explains the observed data. The likelihood function essentially measures how likely it is to observe the given data for different parameter values. By adjusting these parameters, MLE aims to find the values that make the observed data most probable. In other words, MLE finds the parameter values that maximize the likelihood of the observed data. This makes it a very effective method for parameter estimation. For example, consider estimating the probability of getting heads in a coin flip. MLE uses the data from multiple coin flips to find the probability value that makes your observed sequence of heads and tails most likely. This approach is advantageous because it uses all the information available from the data to make the best possible estimates. It is a comprehensive method that takes into account the entire data set. Now that we have a basic understanding of what MLE is, let's dig deeper into the underlying theory. We'll explore the mathematical foundations that make MLE such a robust and reliable method. We'll also see how MLE works in practice, with real-world examples and applications. So let's move on to the basic theory of MLE and understand its practical applications in more detail. The core idea of MLE is to find the parameter values that maximize the likelihood function. We often use the log likelihood function for simpler calculations. Maximizing the log likelihood gives the same result as maximizing the likelihood itself. Let's consider a simple example with a normal distribution to estimate the mean, mu. By taking the derivative of the log likelihood with respect to mu and setting it to 0, we can solve for mu. This process can be extended to multiple parameters. Understanding the theory behind MLE helps us see why it works. Next, we'll look at practical examples to see MLE in action. Let's start with a simple discrete distribution, the Bernoulli distribution. This distribution is fundamental in probability theory and statistics. This models a single trial with two possible outcomes, like flipping a coin. The outcomes are typically labeled as success and failure, or heads and tails in the case of a coin flip. Suppose we flip a coin 10 times and get 7 heads. This sequence of flips can be analyzed using the Bernoulli distribution to understand the underlying probability. We want to estimate P, the probability of getting heads. This probability is crucial for predicting future outcomes and understanding the behavior of the coin. The likelihood function for the Bernoulli distribution is LP equals sign P circumflex 7 asterisk 1P cubed. This function helps us determine the probability of observing our data given different values of P. To find the maximum likelihood estimate, MLE, we take the natural logarithm to get the log likelihood function. This transformation simplifies the multiplication into addition, making it easier to work with. Next, we take the derivative of the log likelihood with respect to P and set it to 0. This step is crucial as it helps us find the value of P that maximizes the likelihood function. Solving this equation gives us P equals sign 0.7. This means that based on our observed data, the best estimate for the probability of getting heads is 0.7. This example shows how MLE uses the observed data to estimate the parameter. It demonstrates the power of statistical methods in making informed predictions and decisions. Now let's look at another example with the Poisson distribution. This distribution is used for modeling the number of events occurring within a fixed interval of time or space. The Poisson distribution is a powerful statistical tool that models the number of events occurring within a fixed interval of time or space. It is particularly useful in scenarios where events happen independently of each other. This distribution has one key parameter, lambda, which represents the average number of events expected to occur in the given interval. Understanding lambda is crucial for accurately modeling and predicting event occurrences. For instance, let's consider we are observing the number of emails received over a span of 10 hours. The observed counts are as follows: 2, 3, 4, 1, 3, 2, 3, 4, 3, and 2. These counts will help us estimate the value of lambda. Our goal is to estimate the parameter lambda from this data. This involves using statistical methods to derive the most likely value of lambda. The likelihood function for the Poisson distribution is given by let lambda equals sign lambda circumflex x asterisk e circumflex lambda x. This function helps us understand the probability of observing our data given a particular value of lambda. To find the maximum likelihood estimate, MLE, of lambda, we take the natural logarithm of the likelihood function, transforming it into the log likelihood function. This step simplifies the calculations. Next, we take the derivative of the log likelihood function with respect to lambda and set it to 0. Solving this equation allows us to find the value of lambda that maximizes the likelihood function. By summing our observed counts and dividing by the number of observations, we calculate lambda to be approximately 2.7. This value represents the average number of emails received per hour. This example clearly demonstrates how the maximum likelihood estimation method can be applied to different discrete distributions, providing valuable insights into the underlying processes. In the next section, we will delve into examples involving continuous distributions, exploring how similar principles can be applied to model continuous data effectively. Now let's explore a continuous distribution, the normal distribution. It has two parameters, the mean, mu, and the variance, s squared. Suppose we have data on the heights of 10 students. We want to estimate mu and s squared. The likelihood function for the normal distribution is complex, so we use the log likelihood function. Taking the derivative with respect to mu and setting it to 0, we solve for mu. Summing our data, we get mu equals 152.5. To estimate s squared, we take the derivative of the log likelihood with respect to s squared and set it to 0. Solving for s squared, we get the estimate. This example shows how MLE can be applied to continuous distributions. The uniform distribution models data evenly spread within a range. It has two parameters, the lower bound, A, and the upper bound, B. Suppose we have data on the time it takes to complete a task. We want to estimate A and B. The likelihood function for the uniform distribution is simple. The MLE happens when A is the minimum observed value and B is the maximum observed value. For our data, A equals 5 and B equals 9. This example shows how simple the MLE can be for the uniform distribution. MLE has several advantages that make it popular in statistics. It is intuitive, providing clear and logical estimates. MLE often leads to estimators with desirable properties like consistency, efficiency, and asymptotic normality. It is flexible and can be applied to a wide range of distributions. MLE uses all the information in the data, leading to more accurate estimates. Despite these advantages, MLE has some drawbacks. Let's explore the disadvantages of MLE in the next section. Understanding both sides helps us use MLE effectively. While MLE has many strengths, it also has limitations. It can be sensitive to the choice of starting values in iterative algorithms. MLE may not always have a closed-form solution, requiring numerical methods. These methods can be computationally intensive. MLE can be biased in small samples. It assumes the model is correctly specified. Despite these disadvantages, MLE remains a powerful method for parameter estimation. In the final section, we will summarize the importance and applications of MLE. In this essay, we've explored maximum likelihood estimation, MLE. We've seen its theory, practical examples, and discussed its pros and cons. MLE is a fundamental technique in statistics for estimating parameters. It is intuitive, flexible, and uses all the information in the data. Despite its limitations, MLE is essential for making sense of data. Understanding MLE equips us to apply this method effectively in our analyses. By mastering MLE, we can unlock new insights and make better decisions based on statistical evidence.